We've talked about what quantities to minimize or maximize, and how to derive them for a certain subset of models, but not how to actually perform the optimization. If we're minimizing or maximizing with respect to some variable's theta, how do we go about finding the thetas which give the optimal points? First, let's explain what we mean by optimal points by looking at an example. Suppose this is a function we're trying to maximize. We're interested in finding the x value which produces the highest y value on this function. We should check the boundary for optimal points if we optimize within some region. In this case, there are no maximum values on the very left and right sides of this function. Optimal points occur among points where the derivative is 0. If we look at all points with 0 derivative on this plot, we'll find a couple different cases. Local minima are where the horizontal tangent lines are shown in red. These are minima within local regions around the point. Local maxima are shown with their tangent lines in green. These points are maximal within local regions around them. Saddle points are neither minima nor maxima, but nevertheless have 0 derivative. These occur when the derivative does not switch signs around a point. When looking for global optima, we can examine each of these points and inspect the boundary of the region in which we optimize, and determine which point is the global maximum. When optimizing in higher dimensions than just 2 as shown, the partial derivatives at optimal points are 0 in every direction, so we should look for points with 0 gradient, and the gradient is the vector of partial derivatives. We occasionally have what's called an analytical solution for finding optimal points. In this case, we can solve the problem directly with a closed-form pen and paper solution. This solution is usually either difficult to obtain or does not exist for most problems. Instead, we may take a numerical approach, where iterative guessing is usually done to get better approximations to the solution. We frequently use computers to give us a reasonable approximation within a short amount of time. These numerical approaches can be applied to most problems, but also have some downfalls and won't give nice mathematical closed-form solutions like the analytical solutions. One of the most common numerical approaches to finding a maximum when we can compute a gradient is gradient ascent. The idea is to pick some initial starting point and then iteratively step in the direction of the gradient, which points in the steepest upward direction at a given point. Each step, if small enough, will bring you to a higher point on the function you are optimizing over. In the equation shown, we start with theta sub 0 as the initial settings, and compute our next approximation theta sub 1, and so forth, by adding the gradient of our function at the previous point times parameter alpha to the previous point. And alpha here is treated as a hyperparameter. Recall from the derivations in previous videos, p of theta given the data under some assumptions can be written as the negative sum of squared errors. We can move the negative to the front of this term to show that this is the same as descending on the gradient of SSE. Gradient descent is used for minimization, and running this would find increasingly better theta to minimize sum of squared errors. What is the effect of this alpha term? Let's look at an example using gradient descent. Larger values of alpha result in larger steps. So if we pick a small alpha, we may take many steps to arrive at the solution, and in some cases, too many to reach the solution in a practical amount of time. If we pick a large alpha, we may end up skipping over optimal points and not find them, or bounce back and forth over an optimal point. So this alpha, again, is usually treated as a hyperparameter and frequently scheduled to decrease over the number of iterations to help the algorithm settle into some region. So so we frequently refer to it as the learning rate. Note that this approach can give a locally optimal point, since you may not necessarily start at the right point to reach the global optimum. So you can't reach the top of the highest mountain by climbing the wrong mountain. There are some special cases in which you are able to guarantee that you'll reach the globally optimal point. Most of these involve convexity or concavity of the function being optimized. The following is called Jensen's inequality. If a function f satisfies this inequality, it is convex. It says that if we take a weighted average of the values of the function at any 2 points, the left-hand side, it should be greater than the function evaluated at the same weighted average of the input points, the right-hand side. The inequality represents the fact that any line between 2 points on the function will be above or on the function in the convex case. So for convex functions, we are guaranteed to find the global minimum. With a concave function, we flip the inequality, and so the line between points will be below the curve, which makes it concave. For concave functions, we are guaranteed to find the global maximum. Most functions do not satisfy Jensen's inequality and are non-convex or non-concave. There may be little pockets where the function is locally convex, and given a low enough learning rate, once you reach such an area, you are guaranteed to reach the local optimum within that region. However, we have no general guarantees of finding the global optimum. We still might reach the same local optimum when starting outside of locally convex regions. So, in the non-convex case, we typically just start our gradient descent at a bunch of different initial settings, let it run, and look at the solutions we get. We may stumble upon the best solution or miss it entirely. If we are just interested in finding a good enough solution, as long as the parameters of the function work well enough to suit our needs, then it's okay.